Start. Maybe running a little late, but we want to get finished before too late. Great to see everyone. I'm Andy Gordon again. Here's our plan. Overall, I'm talking about empowering spreadsheet users with probabilistic programming. So on Monday, I was talking about probabilistic programming in infer.net, and then tabular, which is our DSL that lets people inside a spreadsheet build probabilistic models of their data. On Tuesday, I still finished off what we were saying about tabular, and then got into fabular, which is based on this regression calculus that formalizes how people build these linear regression models. And I explained briefly anyway how that gets embedded in tabular to get fabular. And I said a bit about Stan and its semantics. So in today's session, I'm going to change tack a bit and think about how end users actually encounter uncertainty in their spreadsheets and how they cope with it, and really asking, are they actually ready for probabilistic programming? And if so, what would that look like? But before I get into the details of that, let me just say a bit about the group that I work in at Microsoft, which is called Calc Intelligence. And our slogan is bringing intelligence to end-user programmer, and in particular to spreadsheets. And this is our website, aka.ms Calc Intel. And the work I'm doing on end-user programming fits very much within this team, because we've been working with the Excel team for a few years to well, starting with the concept that Excel is a programming language and seeing if we can make it better. So let me show you. Up there, you can see constructs from Excel. Fonts might be a bit small, unfortunately, but Excel really is a programming language. You know, its formulas have got nested functions and references, so it's compositional. It's got selection, things like if statements. It's got iteration, which is very much driven by the UI in Excel today, but it's based on dragging formulas down. I'm not sure if I can. Oh, that works. Oh, there you go. Oh, much better. Thank you for asking. Yeah, so there you go. There's something like formula. Yeah, these things. So, formula fill down. I'll just point with my finger. That you've got on the left there, you've got a series of strings like hello in B2, and then a comma, world, and bang. And then we've got a sequence of formulas that have been pulled down. One formula that's sort of smart about how it does concatenation, and it builds up a sort of a bigger and bigger string on the right. So you can do this in a kind of crude way, but it's not sort of ideal. So the goal of the... Okay, now I do want to move on. Why isn't that working? Okay. And in fact, they have great many people use Excel, many hundreds of millions, and arguably that's way more than a number of people who consider themselves professional developers. So there seems to be a bit of a limit on Excel's potential. You know, there's no real notion of abstraction of formulas, like being able to define new functions from formulas, and no real sense of data typing. In fact, Excel is kind of notorious for not really understanding the types of data. So our research aim has been to remove this glass ceiling that limits what's possible in Excel, that limits their scope and reach of what a domain expert can do in Excel. And we've got there's sort of two pillars of what we're trying to do. One of them is to make Excel functions reflect the abstractions of end users. So that means that we can actually take bits of grid that define some computation and give them names so they can be reused, so that we can actually enhance the formula language within itself without having to resort to external programming languages like VBA or JavaScript that can be used to script Excel. That's one concept. And I'll talk a bit about something called sheet-defined functions, which is one way we aim to do that later in the talk. And then the other point is to make the data values in Excel reflect the concepts, the data types, if you like, that people actually use. So we're adding things like arrays, vectors, records, and even new domain-specific data types to Excel. So you can have composite things sitting in a cell. And some of this is in the works. and it's not really done yet, and I can't really talk about how it's going to appear in the product, but some of it has started to appear. Okay, see if I make this bigger. This is really cool. Yeah, look at this. Man. Please just stay. Yeah. Oh, it's not going to animate. Well, you can't have everything. Oh, man. It's busy animating away. The point about this... I'm lost now. All right, come back. Right. Up there, you can't really see it. I'm going to give up. But you can actually have a single formula there that is a whole array that sits in the cell, and then we call it spills out. So you can't really see it, I'm afraid, but there's a list of names there, and here you've got them sorted. But it's a single formula. This hasn't been written by drag filling a formula down like I was showing. So that's really cool. And then here you've got a unique function that takes a bunch of names that have some duplicates, and it produces an array that has all the unique values. And then this one is doing filtering. So you've got an array, and it's filtering just on the people here who prefer veg. So we're having these like array processing functions that are actually now already released. Actually, they're not. Well, they are released to some customers. So that's one point. The second one is we've now got smart data types. So things like stocks and cities and countries are basically records of data about, say, a stock, like the name of the company, like the current price, maybe limit, the 52-week high, 52-week low, and so forth. Data structures like that, records, can now sit in cells in Excel, and we've got functions to extract their components. So this is a big step forward for Excel, which previously has only allowed text or numbers to sit in cells. So now we can have composite data sitting in cell. There's lots more to come. There's a blog that we put up at POPL. So if you go to, aka.ms/POPL, this is from a few months ago, we had a blog post that I co-wrote with Simon PJ, about what we're trying to do in the project. And this is a picture of some of the members of the team. And we're looking for interns. I'm very happy to speak to anyone who's interested in coming and helping turn Excel into a really high-powered programming language. Nima, who's at the back, is about to start an internship with us next week. So people in this community are really very welcome. So please do speak to me about it. So that's a bit of context directly relevant to what I want to say about end-user probabilistic programming. So let me start with a quiz. Probability quiz, so you need to concentrate. Your project is composed of 4 independent and parallel subprojects, okay? Each subproject will take between 1 and 2 months to complete. And so that means that each one has an average completion time of 1.5 months. Okay? So then the overall project, how long do you think that will take on average? And it's a multiple choice, so it's pretty easy. It could be less than 1.5 months. It could be 1.5 months, or C, more than 1.5 months. So who is thinking A? Who is thinking B? Quite a few, about half the room. Very good. Who is thinking C? A little bit more. Even better. That is the correct answer. It's a bit more than the average. So why is that? Well, the mathematical answer is something called Jensen's inequality, which I recommend you look up in Wikipedia, but I will not go into the details of that. That's the proper answer. The more intuitive answer is that you can't finish your project until all of your sub-projects are finished. And finishing any one of them in 1.5 months is like flipping a coin. And so finishing all of them in less than 1.5 months is as likely as flipping 4 coins and having all of them come up heads. So it's a very small chance that they will all of them be finished in less than 1.5 months. So that's why it can't be 1.5 months. And in fact, it's very likely to be more. So this is an example of what is known as the flaw of averages. And this picture is another example of the flaw of averages. This is a river whose average depth is 3 feet. And it's showing a statistician drowning in such a river. And the flaw is to consider a distribution as if it was exactly its average. And so the guy is drowning. So the flaw of average is the mistake of treating a distribution of things as if they were all the average. And this will turn out to be a good, one of the sort of classic arguments for why end users, when they're considering sort of business processes, business decision making, they should take account of uncertainty and deal with distributions, as we've been talking about. But before I get to that, I want to just give a bit of context on spreadsheets, and then I'm going to talk about some of these probabilistic decision-making tools that are actually have been built on top of spreadsheets, and then I will give a summary of how the talk is going to proceed. So this is a slide just introducing spreadsheets. This is actually the 40th anniversary this year of the launch of VisiCalc, which was the killer app of the microcomputer revolution. Steve Jobs is down on record in saying that if VisiCalc hadn't been written first for the Apple II, then Apple wouldn't have been the company that it was. Possibly it wouldn't have been, a company for very much longer. I mean, it really drove purchases of Apple IIs, and it's remarkable. The equivalent, I think, an Apple II. In today's money would have been about $5,000, and people bought Apple IIs in order to build spreadsheets. It's hard to imagine how hard it is to run a business if you don't have an electronic spreadsheet. People used to do this. They had big sheets of paper with grids, and they would be keeping track of their accounting and making business decisions, and it was pretty hard. And so people just loved having spreadsheets. So what I'm showing here is a bunch of formulas, and I'm just taking the opportunity to illustrate the flaw of averages in these formulas. So what is a spreadsheet? It has a grid, and then cells can contain either constants or formulas, and formulas can refer to other cells. And of course, one of the great things about the spreadsheet is that you can calc it once, and then if your formula depends on something that you subsequently change, you want to do a what-if calculation, you're thinking about your business plan, and you decide to change the price you're going to charge, then the thing automatically recalcs. Amazing experience. What I'm showing here is my 4 projects. So A, B, C, and D are the 4 projects, and I'm modeling the time it takes as rand, which returns a number between nothing and 1. And I'm adding 1 to it, so that's giving me a project that's going to last between 1 and 2 months, with the average being a half. And what I've done is done a drag fill, which you can't see, but I've done a drag fill of that formula down. So these are all copies of that guy, and the same with all of those. And down here, I've taken the average of those ranges, and you can see they're all kind of round about 1.5, but because we've only got 10 samples, there's quite a lot of variation in them. And then over here, I'm doing actually the calculation. What is the max? How long is the project? If you like, each project, each row is like a particular trial of these 4 projects running, and I'm taking the max of the 4 of them up there, and eventually taking the average. So this is the average time that I'm getting from my spreadsheet, like 1.78. So it's more than 1.5. On the other hand, the max of the averages, which is the flaw of averages, gives about 1.5. So this is illustrating the flaw of averages numerically. And if I had this live and you tap F9, it's really cool. You just keep on getting new values of rand, and you're drawing new samples, and you can sort of get some confidence in whether this was, or get more confidence in what the model is saying. Okay, now, using rand so Monte Carlo simulation is just simply where you run a computation many times. Probabilistic programming, randomized computation many times is a way of viewing the distribution. Probabilistic programming, as I've been saying, also involves conditioning using the observe statement and things like in fun that I was showing you, or it's where in things like Stan or tabular, you give explicit models of data that has been observed, like the Y we had in the linear regression examples. And when you do that, you're actually doing Bayesian inference, and you're conditioning the parameters, and you get posterior parameters that you've learned from the data, where, for example, the slope and intercept in these linear regression examples that I've done. So that's real, if you like, full probabilistic programming, where you both have the generative process, the randomness, and you also have the conditioning on the data. Now, what we're doing here, I think it's not really fair to call it probabilistic programming. It's definitely Monte Carlo simulation, and in fact, it's really what you're doing when you're drag filling the formulas down is really defining a simple algorithm. In this case, really just you're repeating the calculations. And the idea of probabilistic programming is you don't define the algorithm, you define what the probabilistic model is, but you don't sort of do the explicit iteration. So I think it's too much to say that doing what I've done there actually counts as probabilistic programming. And this is worth saying because this kind of Monte Carlo simulation has happened really from the start of spreadsheets. So people were doing this I looked at VisiCalc, I'm not sure, yeah, I think VisiCalc had RAND in it, so people were already doing these Monte Carlo simulations, quite possibly from 79 in spreadsheets. So I wouldn't say that is probabilistic programming. On the other hand, and this is a thing that came as a bit of a surprise to me, steeped in the academic literature on probabilistic programming languages, there have been these tools, add-ins, such as @RISK and Crystal Ball, that let you do actual, what I would say is probabilistic programming in spreadsheets. And they would, if I go back to this, they would let you write a situation where you just write the top line, and then they would automatically, using VBA or something, animate the spreadsheet and do multiple calculations. And then do this, so no drag fill is required. You just write your model in this row, and then it would repeatedly calculate it for you, and then come up with distributions of what is in, say, in E1 or in E10. Now, I don't have a sort of picture of that, but you can take my word for it that that's how those systems work. So I'd say that is probabilistic programming, although without actual conditioning in general. Although, in fact, if you look into it, sometimes they did do conditioning. So I think there's a reasonable case to be made that that was probabilistic programming. And here is a user. So we started to talk to users about how they actually do modeling. This person, Peter, is a friend of mine, and he's a consultant, and he actually helps big oil companies and other big firms do risk management on large projects, where a lot of money is at stake. And so I give you a very baby example of like 4 projects, but obviously if you're exploring for oil or something, you're kind of, there's a whole lot of things you need to sort of, put up that, over many months, even years. And they build complicated models of the different things that need, the different parts of the project and their dependencies, and then they use this Monte Carlo simulation in @RISK to actually to figure out how long they think it's going to take. And I love this. He came in, and I'd read in theory about the flaw of averages. There's a book called The Flaw of Averages that is by a guy called Sam Savage that I also spoke with. And he makes this very eloquent case for the mistakes people make. But I still felt this was rather theoretical, the guy saying this. But it was kind of interesting to me to meet someone. And he actually said, I actually didn't even prompt him for this. He said, actually I've got this here. He said that they very commonly ask people if they're going to estimate how long a project is going to take, is to define it as a triple. And for example, 1, 2, 3. And the idea is that 1, this is like an estimate of how long it's going to take, where 1 is the minimum time, 2 is like the most likely time, and 3 is the maximum value. And then he drew this picture and he said, well, what it is what's called a triangular distribution. Okay, and this is like the density of the triangular distribution. So that's the most likely time, that's the minimum, and that's the maximum. And this is the notation for it. And he volunteered to me, said, did you know that people don't get this? That if you take 2 of these together and take their maximum, it's not the average. It's more than it. So he absolutely has encountered the flaw of averages in reality. He also. Actually, he didn't tell me this. Someone else told me this. So Frank Wood is this advisor of some of the folks at the back, professor up at UBC, used to be at Oxford. And he told me that he'd heard from the guys at Palisade who make @RISK that they have about 500,000 users, which is interesting. So there's a lot of people do this probabilistic programming. So I'm going to give you a comparison here. Probabilistic programming since the 80s. So in fact, since about 87, this tool, @RISK, came out, and Crystal Ball was around about the same time. And then a little bit later, but definitely later, probabilistic programming languages started in 89 with the Bugs project, and then they've had these other systems, of course. And then more recently, in the last 3 years, there have been some spreadsheet-like systems that explicitly do probabilistic programming in spreadsheets. And so one of them is very cool. This is open source, something called Guesstimate. If you go to getguesstimate.org, there is this open source graphical spreadsheet environment. It doesn't exactly use a grid and grid referencing. is pretty much a spreadsheet where you can put uncertain values. Let's see if I can magnify this. Yeah, there you go. Man. Well, you can put uncertain values in the cells. Heavens. I should stop trying this. I'm just too much of an optimist. Oh, now it's decided to hang. Great. Come on, don't do this to me. Is this? Basically, you can put, I'll give up again, but I hope you can sort of see that there's uncertain values with with histograms of the distribution in the cells, and they're doing calculations on them. And then Frank's team in Oxford, he had a spin-out company called Invrea that actually did Bayesian update where you wrote your probabilistic program using formulas in Excel, and he had a new function called actual, which was a way of doing conditioning on the data. And so they built that, which is very interesting. So probabilistic programming has happened in spreadsheets from pretty early on, and now includes full Bayesian update in spreadsheets. And usage-wise, I find that pretty interesting too. So there's a lot of spreadsheet users in general. I think a conservative estimate is tens to hundreds of millions of people use formulas in spreadsheets. I should note that a lot of people who use spreadsheets don't use formulas. In fact, it's probably less than half. A whole lot of people use spreadsheets and simply use them as a way of viewing data. They're not actually writing lots of formulas. But still, a lot of people can write simple formulas in spreadsheets. I would say that's a few orders of magnitude more than the number of people who actually do probabilistic programming without conditioning. So like Peter Adlington, the people who use at risk. So it's a tiny fraction, like probably less than 1,000th of spreadsheet users use tools like at risk and are doing probabilistic programming. So I'm afraid it's a bit of a minority interest at the moment. But still, I reckon that is still maybe 10 times more, and that's being a bit conservative, than the number of people who actually do probabilistic programming in full-on probabilistic programming languages like the ones I've been speaking with. So in a way, I'm very interested to see if we can sort of go up the stack and get more people to do probabilistic programming. So let's talk. Probabilistic programming is about helping folks make decisions under uncertainty, and we're going to examine how people actually well, I'm going to ask whether I can use probabilistic programming or put probabilistic programming in the hands of people who are trying to make decisions under uncertainty. And the way I'm going to approach this is I'm going to, first of all, I'm going to start with some technical solutions. And there's two. There's the idea of uncertain values, where you can put a probability distribution in the cell of a spreadsheet, like in at risk. I'm going to talk through the possibilities around that. And then I'm also going to show you how these sheet-defined functions that Simon and others proposed many years ago as an extension to spreadsheets and aren't there yet, how we can actually use sheet-defined functions to model uncertainty. And then I'll turn to this interview study that we did, looking at the kinds of uncertainty that folks actually encountered, and then I will draw some implications. Okay. So, part one, uncertain values. And this is largely based on a PhD from Queensland University of Technology in Brisbane by Alexander Street, called Encapsulation and Abstraction for Modeling and Visualizing Information Uncertainty. So his concern was very much what I've just been describing. How can people cope with uncertainty in spreadsheets? So the way I'm going to explain his solution is with a simple budget spreadsheet and show how the uncertainty in this spreadsheet can be modeled in different ways using uncertain values. And I'm going to speak in terms of a fictional end user called Clara. So Clara's an end user who's confident about modeling things with simple formulas. She's confident with things like arithmetic, plus and minus, applying a sum formula to a range, but I'm not assuming that she's more sophisticated than that. There's actually a lot of users who are kind of at that level of sophistication. They don't know about fancy, or they don't ever tend to write very fancy nested formulas and only use a handful of formulas. And yet you can do an awful lot of work in a business context using simple arithmetic. So this is the budget here. So she's got some income for a particular month, and then she's got a table of expenses, rent, commute, sofa, and utilities, and she's trying to decide whether to buy a sofa or not. Yeah, it's her choice. And it's going to be 700 more than usual. And she's pretty sure about her rent and her commute, but let's say she's rather uncertain about her utilities bill. Okay, so that is a very simple baby example, but it will allow me to go through it in detail. And so she has a model here where she totals up her expenses, and then she subtracts the expenses from the income, leaving a balance. And she's concerned about not going overdrawn. So that's her simple budget over here. And then I've written it out in a notation we call calculation view. So we've actually built, I won't go into this in this talk, but as part of our Calc Intelligence project, we built a tool called Calc View, which lets you view the formulas of a spreadsheet as if they're a program. And so, in fact, if you gave it that budget, it would show you this, more or less, where it shows interesting ones are the ones with numbers. So in column F, you've got F4 is 2000, F6 is 1100, and so forth. And I've left blank. F9 is, she's not sure about that. Right, so that's my scenario. And so back to Streit, and he had this idea of uncertain values in cells. So let's talk about that. 3 parts to it. The first is that a user can input uncertainty in some way into the cells. And he was quite abstract about what uncertainty could mean. And he has got, and so one, well, I'll go through the different possibilities in a moment, but he didn't limit himself to probabilistic uncertainty. So he assumed that there could be some kind of textual notation, such as a numeric range. You might say 5-7 to indicate that this number is somewhere between 5 and 7. Or maybe you might write a probability distribution. He considered Gaussian distributions. Now, although behind the scenes, there's some kind of formula, or at least the way I'm kind of reconstructing what Streit's proposal was, is that behind the scenes there's an actual formula that produces a value in the PL sense that represents the uncertainty. But don't get me wrong, I'm not assuming that Clara has to write the formula. There could be some kind of UI that would let her say, I'm uncertain about this number, and then let her give a range graphically or what have you. But I think in this room, we can take that for granted, and I'll just show you the formula that's behind the scenes. But I want to emphasize, I'm not assuming that the person is really sophisticated about using formulas. The second point is that the uncertainty information propagates through formula evaluation. So in a technical PL sense, we'd say that we've got an effectful computation here. And then thirdly, when an uncertain value shows up in a cell, the user needs to be alerted to the fact that they're uncertain. So a simple thing we might do is show the most likely value and put a twiddle symbol beside it to indicate the thing is uncertain. But there's other things we might do as well, like in the guesstimate screenshot I showed you, where it shows you a little histogram of the likely values of the cell. So essentially, this is a computational effect for uncertainty. And there's a paper that hasn't been written that would be a technical paper that would take these uncertain values and give a formal semantics using perhaps monads and what are they called? What's the baby form of applicatives? Applicative functors instead of monads. But I would wait until I've finished the talk before you go and write that paper. But it would be a fun paper to write, I'm sure. Streit himself considered estimates, intervals, and parametric distributions. I'm going to consider a different collection of primitives to consider. So estimates, this is the thing that Streit considered. And the idea here is that we introduce some sort of tag. So Clara just tags the value as being uncertain, and then propagation will propagate that tag or label. So this is almost like an information flow system, that certain values will be tagged as being uncertain, and then anytime any computation meets the uncertain value, it itself becomes uncertain. So it's a kind of tainting, if you like. So we assume there's a formula called estimate 100 that would tag 100, and then she puts F9, puts that into F9, and then F10 is right. The formula F in F10, its value is now tainted with estimate, and the same with the eventual balance. Now, in this case, this example, she maybe doesn't get a lot of value from that because she knows that the punchline is going to be uncertain. But you could imagine in a much larger spreadsheet, if some values are uncertain, it'd be good to know, what that taints. So I think there is some value in this, but frankly, not a huge amount. Then there's probabilistic. So this is where the uncertain value is represented as a set, or really as a tuple of scenarios, if you like. Think back to Peter Adlington. He got his customers to talk in terms of the best case, the worst case, and the most likely case. Having now spoken to a lot of financial modelers and other people who use spreadsheets, I can tell you this is a very common way of looking at uncertainty. You don't actually know how likely the worst case is, but you know it's probably, whatever it is. And this, I think, is really quite attractive. So we could have a formula scenarios that takes a tuple of values, and the UI could help Clara drop that into cell F9, and then this propagates. And what happens is that the sum here applies to those numbers together with scenarios, and then basically does this sum for each of the scenarios. So you get 3 different scenarios. So if utility is as low as 50, then the overall expenses are down at 1935. If they're as high as 150, then this will go up to 2035. Okay, so it's just threading through 3 different scenarios through the calculation, and then the same applies to the balance. And then she can look at the 3 possibilities and say, okay, well, the worst case is minus 35. That's not good. I mean, that would be a going over drawn, which she wants to avoid. On the other hand, she might see that, well, what's most likely is 15, and maybe she's prepared to take the bet at that point. But she doesn't get any probability associated with how bad the scenario is. This is actually an alternative to existing techniques. So for one thing, she could simply duplicate the calculation, which is quite common in spreadsheets. In fact, arguably that's one of the great appeals of spreadsheets from the start, was that it's very easy to duplicate bits of calculation. So in a way, this is like the scenarios approach is like a fancy way of replicating what is already possible. So here you've got a best and worst column, or a best and worst table tab, where you copy the whole sheet. Excel and other tools, other spreadsheets have tools like this, the scenario manager, that can take a bit of grid and then take some cells and then change them systematically according to different scenarios, and then produce a report. It's an alternative to doing things like that. I think arguably it's better than the scenario manager, because this is not integrated with recalc. And if you've got complicated spreadsheets, and you've got many scenarios you're considering, I think it's probably better than duplicating the spreadsheet. And for one thing, you're not duplicating the model. So if you want to subsequently make changes to the model with these uncertain values, then it will apply to all of them. Whereas obviously, if you make copies of a spreadsheet like that, it's very hard to keep them, in sync. Finally, probabilistic uncertain values. So these are like, before it was like sets of values, now it's like weighted sets of values, if you like. So we could introduce a function, triang, or dis.triang, that constructs an uncertain value corresponding to a triangular distribution, for example. This is just one example. I mean, there's lots of other distributions that we could build in. And so we give the sort of least value, the maximum value, and the peak, the mode value C, and then drop that into F9. And now this will propagate. And so you get this triangle. It turns out in this case, these sort of linear operations on the triangular distribution sort of turn a triangular distribution into another triangular distribution. So we're in a happy case where it just it stays as a triangular distribution, and you get in the end this distribution at the end, and then you can actually ask what's the chance of an overdraft, and get back the value 25%. So now finally, this is like an example of probabilistic programming, where she has really put in some assumptions there, and she gets a probability out for how likely the overdraft is. Or Peter, his customer, would get like some sort of probability at the end. Will my whole gigantic project come in on time, on budget, for example? So this is the baby version of the more complicated things that he would do. And then, of course, it's a spreadsheet, so you can go back and tweak this, and then it will all recalc. So that's cool. How might you implement this? Well, one idea is basically to have to represent the uncertain value as an array of samples from the distribution. I mean, sometimes you can just use this parametric distribution, meaning it has some parameters, and then do arithmetic directly on them. But very often, the distributions change shape when you apply arithmetic to them. And so that doesn't work. So a versatile way that works in all cases is to effectively take the Monte Carlo simulation and squish it into a cell in the sheet. So the idea is that morally you can think about the calculation that you're getting from uncertainty as being equivalent to repeatedly doing sort of random or doing recalcs of the spreadsheet where those distributions are just random draws. And then what you actually do instead of that, which is roughly what those old spreadsheet add-ins like @risk did, you take advantage of the fact that we can do now in Excel that we can hold a whole array in a cell and put an array of samples that correspond to A1 from all those sheets, put that in a single sheet in a single cell. So that's known as a SIP, which is a term, it stands for a stochastic information packet. So we can use SIPs to represent uncertain values. I mean, that's something we've added. Street wasn't proposing that. So then, how would this help? So let me show you another example of the flaw of averages, just to hammer home the idea of using this to make better business decisions. So this is a classic example from textbooks about doing sort of Monte Carlo simulations. Sarah.
Sorry, this was a question about the previous example. Does the
Sure.
user need to know that the function is called this .triangle?
No. No, the idea is that there'll be some kind of UI to help her introduce that. So she would need to know, or ideally the spreadsheet would inform her or give her a choice, do you want to make this value uncertain? And then sort of guide her through how she wants to represent the uncertainty.
So you would guide the user through how they want to represent or what model they want to use, or distribution they want to use?
Yeah.
Okay. Because I guess if you, it seems like reasonable to assume that clients from large industries would be familiar with the names and parameters of the distribution, but not so for end users.
Absolutely, yeah, yeah. So I'm not showing UI here at all, but we've thought about what the UI might look like. But I'm just avoiding that for this audience. But that's totally on point. Okay, so here's here's an example. How many Valentine cards to order? So I'm not proposing you're going to buy 1 million cards to send yourself before you get your leap into the wrong conclusion. This is more like you're a business and you're deciding in January sometime how many Valentine's cards to buy. And it's an interesting challenge because these are like a perishable good. After February 14, you're not going to sell many Valentine's cards. So it's a little bit of a challenge of how many you buy. Because if you buy too many, if you buy too few, you've left profit on the table because you've got demand that's unmet, and so you didn't get any profit from it. If you buy too many, then you maybe won't make a loss, but you cut into your profit because you end up with this unsold stock that basically depletes your profit. Okay? Supposing we're in 2017 and we've got these sales from previous years with this average around about 1 million. If you build a spreadsheet where, I've got a number of choices I might make, 400,000, 700,000, and so forth, and then I've got a cost per card, a price per card, so the cost is like the number ordered, or overall cost is, well, you can see what it is, and then the profit is, based on how many you actually sell, what your profit is going to be, and then the net profit is that minus the cost of the cards. Okay, so they're sort of taking into account so this is the gross profit from your sales, and then the overall net profit is that minus any unsold items that you get at the end. Okay, so that's fine. So if you didn't have uncertainty at your disposal, you would do the calculations, and you can see that the net profit is highest, 513,000, higher than this number or that number, for ordering 1 million. So you'd order exactly the same as the previous year's demand. But at this point, you'll be alert and saying, Andy, but the flaw of averages, you shouldn't be treating a distribution like what the demand is as if it was the average. You're going to make a mistake. Remember Jensen's inequality, you should be saying. But it's kind of hard for Clara without uncertainty to do that kind of calculation. But if Clara does have uncertainty, what she can do is look at the averages, the distribution previously, take the average but also the standard deviation, and then she can write an uncertain value there that's given by this formula, so dis.norm, and she puts in B12 and B13, which are the average and standard deviation. So, and she gives it an n, like n equals 1,000, and so that's going to be 1,000 samples from this particular distribution. So she makes the assumption that it's Gaussian distributed, which is an assumption for sure. But she's basically got a probability distribution sitting in that cell. And now the exact same model she had before, she has to change no more formulas, recalcs. And now you see that the gross profits have got this twiddle symbol, meaning that that's the expected value of these uncertain values. And then these net profits also are uncertain. And what you see is that the net profits here are lower than they were before. Okay, here I'm comparing the decision. So the previous decision you'd have made was to order 1 million. But if you actually look at the profit that you expect to get, it's actually lower there than for ordering 850,000. And the intuition for this is that you're thinking about an uncertain future with uncertain demand. So let's see. So some of the time you get less demand than you expect. And so at that point, you make an actual loss because you've got some unsold stock. So that's an actual loss. On the other hand, sometimes you've got higher demand than you were expecting to get. And that's a point where you kind of have this missed opportunity. You've left some profit on the table. But unfortunately, this hypothetical profit you didn't make doesn't balance out the actual loss you did make when the profit is lower. And so that's when the demand is lower. And so that's why the net profit is actually below what you thought. And so it means that if you would, so the punchline is you make a different decision if you took into account uncertainty, and you'd actually make a profit. A higher profit. I think I did the calculations, and it was actually about a 10% higher profit you'd make if you had uncertainty. So that's great. You make better decisions with uncertainty. And so this is the classic case for why you should have uncertainty in general, but and that's specifically to why you should have it in spreadsheets. Oh yeah.
In the case of the Valentine's card, it could be that you're sold out, right?
Mm-hmm.
And then you would like to represent the amount of cards you were missing, because then you will have 10,000 cards sold that year,
yeah,
which will go into your average. But your actual demand wasn't 10,000; it was a lot more because you ran out. How would you account for that? How would you allow an end user to account for this kind of missing data, because they didn't write down how many angry customers there were?
Oh, but the end user could figure that out. So here I guess I'm assuming all they've done is record the sales. But I don't know how practically a business could keep track of that. But potentially they could if it's an online store, they could get clicks they were unable to.
So how would they go about guessing that or taking that into account?
Well, if you don't have the data, they wouldn't be able to. But I think the they would just need to start tracking the data. So these are some screenshots from Street's PhD, and in particular showing visualization of uncertainty. I just want to emphasize that this is a really important topic, but unfortunately I'm not going to cover it. It's out of scope. But if we're trying to deliver uncertain values to end users, we need to have ways for them to visualize it and understand what it means. And there is some research on that, but I'm not going to cover it in this talk. But you can't see it, and I'm not going to try and magnify it, but he had some nice screenshots here of a spreadsheet with uncertainty with intervals in it, and indications of most likely value and so forth. He also did a user study, which is the first one I'm aware of actually in this sort of space of probabilistic programming for end users, and he got very positive evaluations. The thing I'm rather concerned I mean, I think it's good that he did this, but he only had 3 people he spoke with, which is a bit small. I mean, he didn't claim any numeric results from it, but he did put up some sort of quantitative things, and I think this is a bit of a weak user study. So he's got things like, where are we, 1, he's got stuff like, I would use intervals in Microsoft Excel if they were supported, which I'm very interested in, 10, and yeah, they loved that. They were very keen, and I would model uncertainty more often if I had these features available. So his 3 people were very positive about it, which is good, but I want to stand before you and just, I've been working with HCI researchers on this, and they tell me, Andy, don't ever do a user study like that. I don't want to give Strike a hard time, particularly, because he was early on. But just to call out to you, there's a couple of interesting papers in HCI. One of them is something called participant response bias. And they found that respondents are about 2.5 times more likely to prefer a technological artifact if they believe that it was developed by the interviewer. Even when an alternative is identical. So I'm afraid that's exactly what Strike did. He invented just the one thing and asked users whether they liked it. And they did. Maybe they were just being nice. So that you need to really have some alternatives to put before users. And indeed, there's another paper that argues you should really put 3 different designs in front of users and then get people to choose between them. So you get some sort of comparison. And they'll be equally biased in favor of all 3. So you can go look at these papers. They will. I'm a bit late in putting all these my talks on the PDFs of my talks on the web, but I will do that later today, God willing. Okay, that was extension 1. The second one is sheet-defined functions. I'm losing track of time. I'm trying to. Okay, I'm almost an hour in. Okay, no, that's probably on track. Good. Sheet-defined functions. So we love sheet-defined functions. So Simon P.J., along with Alan Blackwell and Margaret Burnett, had a great paper, visionary paper, back in 2003 at ICFP, introducing the idea. And this is great. This is real functional programming in spreadsheets. I love it. This actually was what got me excited about working on spreadsheets. So a sheet-defined function f is specified by body, which is a piece of grid. Some inputs are defined by ranges in the body of the grid, and there's an output that's also defined by a range in the body. And then if you have a function call like this, then notionally you make a copy of the bit of grid, the body, and then you take the values and paste them into the input ranges, that you recalc or evaluate the body, and then you look at the output range, and that's the answer, and you return it. So, for example, Clara could could turn her budget into an SDF. Now, peace, we'll have a UI to define the sheet-defined function. I'm not expecting Clara to say function budget brackets F9, but I think in this room, I think you can see what I'm on about. That this is the body of the sheet-defined function, and I've labeled F9 as the input. So the utilities bill that she's uncertain about, she's going to make the argument to the SDF, and then she's going to return F12 to G12, which is the balance at the end, together with a flag that is saying whether or not the balance has gone below 0. In other words, whether she's gone overdrawn. Okay, and so that's actually going to be returned as an array. And so now the cool thing is that we can sort of replay what Stripe was doing. So we can do what I would call this a possibilistic model, the multiple scenarios model, by doing 3 different function calls based on different data. So in this case, we've got she's got her sort of worst case, or our best case, worst case. Sorry, best case is low in this case, most likely, and then worst case, and then we call the budget function, and it works by making copies of that grid, recalcing it, and then what it returns is an array. And like in that video I showed at the start, the array spills out. So the 2 answers come out here, and so you get this nice table just by drag filling this formula. So very simply with an SDF, you can get the effect of multiple scenarios. And then for doing probabilistic reasoning, we can again, we can construct one of these SIPs for a triangular distribution and put that in a particular cell. And then we can map the budget function over this SIP. And now what we get is something like this. so this is a bit like those Monte Carlo simulations in that first grid I showed you, where, for each possible value of the utilities bill, I get back a pair of the balance and whether she's overdrawn. And what I've shown over here is some functions that summarize the SIP. So this is the summary of the balance, and it's got 1,000 samples, and you see it's got a min, a max, and a mean and a median, and the same for the overdrawn column here, this array. And she'd get back that the mean was 26%, which is the same as she got before. Now, I think this probably would be beyond Clara to do a VMAP. But again, I think a little bit of UI could help her. If she says that a bit of grid represents an uncertain model, then we could construct these formulas for her and tidy up in various ways. Now, using RAND like this, or using RAND as in Monte Carlo or in this way, again, is not really probabilistic programming, because doing that map is effectively the algorithm. But it's like a new idiom. We could use SDFs to avoid this flaw of averages. Okay, I'm going to take the break right now, say for 5 minutes, and then when we come back, I'll go through the interview study and end the course. So let's just take 5 minutes and be back. Well, I'd say at 10 to 5. Great. Let's get back to it. All right. So the interview study, we wrote a paper. It's not yet published, that I've got here, which I can. You're welcome to take a look at, or I can send you. In fact, it's on web. It's on the web on archive, and again, I'll put it in the notes. Which is this paper here. That's the details there, and we use a technique called thematic analysis for doing the interview study. So let me just describe what we did. Research questions: what types of uncertainty do spreadsheet users deal with? How do they manage these various types? And the way we approached this was that we conducted these semi-structured interviews with 11 participants who walked us through the spreadsheets. And we took audio transcripts of these interviews, and then they were used to, as part of the analysis, to look at different types of uncertainty that people encountered. And then we identified, using this thematic analysis, themes amongst the different moments when uncertainty was discovered, and grouped them into 6 different types. And then separately, we also looked at the kinds of strategies people used to cope with uncertainty in their sheets, and categorized them as well into 6 different categories. I should emphasize that this thematic analysis is very much qualitative, and it's quite respectable, widely used technique in psychology. But it's not like coming up with some hypothesis and then trying to test it and figuring out p-values to see whether you've refuted the null hypothesis. So it's not a sort of quantitative method like that, which to some extent justifies having a relatively small number of participants. It's the kind of thing, the more participants, the better. And in a way, this was like some initial study to see what we would find. Some details about the participants. They came from different areas of industry: finance, construction, IT consulting, oil and gas industry, and so on. And I can just read out somewhere. There was an independent accountant, a model developer, accountant for a bank, a software engineer, model developer, engineering consultant, finance manager of a public school, finance risk manager, oil and gas company, spreadsheet designer for financial services, then an academic research associate, and academic research fellow. And they had, some of the spreadsheets were as small as 40 rows and some had thousands of rows. We recruited them using convenience sampling, which is a fancy way of saying that you kind of use your social network and email and ask if people know other folks and so forth. And we were asking them if they dealt with uncertain data. So I guess one point here was that we were looking for probabilistic situations. We were thinking about probabilistic programming as a way of helping with uncertainty. So we asked people, have you got uncertain data in your spreadsheets? So that was quite deliberate. It turned out that the ones we ended up with were all for work purposes, but that wasn't a deliberate filtering. And we did give some examples that might involve uncertainty, such as budgeting, planning, business forecasting, and so forth. And the interviews took about an hour, and folks got a voucher in return for their time. The procedure was that we asked people to bring their own spreadsheets, well, one or more of one spreadsheet that contained uncertain data. And then there were 3 parts to the semi-structured interview. In the first part, we asked them to talk about their work and how uncertainty and spreadsheets were part of it. In the second part, we asked them how they got insights from uncertainty and what sort of strategies they use, because we wanted to categorize what the strategies were. Excuse me. And then in the final part, we actually looked at specific spreadsheets, and we actually retained the spreadsheets with their permission, which we used as part of the analysis. And we audio recorded the sessions so they could be transcribed. So those were transcribed, and then we used this inductive approach of thematic analysis, which basically meant that we sort of separately looked at the transcripts and looked for particular themes, which we sort of tagged, and then we tried to collate them together. And so this is called coding, where the code would be, well, I'll show you the codes that we ended up with. The codes are sort of tags representing, for example, different types of uncertainty or different coping strategies. And then we try to find, we identified key aspects of the sheets and the work practices, like what the purpose was that they were dealing with. One thing we discovered was the different roles that spreadsheets played. And so we've got 5 here. I think these are arguably a little bit overlapping, and that maybe is in the nature of this sort of thing. We didn't start with particular categories, so stuff is a little bit fuzzy to my mind, but it was interesting to do this. And also we can't be particularly quantitative about this. We only have 11. I will be on one point quantitative, but I won't say which of these are, whether it's particularly significant, whether there were many database uses versus many notepad uses. But database is where there's not really any formulas, but just a lot of data about how the company worked. Or it could be an analysis of some specific aspect, say, of how a company works, like a business plan that you might use as a template and then replicate for other situations. And here it's interesting. We asked about uncertain data, and the person discovered that the actual template they were using itself was uncertain, that they didn't quite understand how some of the calculation worked. So it started to become clear that spreadsheets often are long-lived, and maybe one person authors them and then other people make use of them. And sometimes the person using them is a bit fuzzy about exactly how the thing works. Then the original person leaves, and so you're stuck with this. I mean, it's the same as with professional coders, but you find the same thing with spreadsheet users. It can be used as a calculator and analysis tool. So you're actually building up a lot of formulas to make predictions, as a sort of notepad to sort of understand a project. I'm not sure if there's a really firm distinction between notepad and calculator and analysis tool. We got this screenshot which showed up some actual confidence numbers. So this person was trying to predict how much they were going to charge for a software development project, and so he's been putting down a number of work days, like 2 for this and 3 for that, and he's indicating that he's pretty confident that it will take, he's 80% confident that it will take 2 days for this task, building this main website. But then something he's called a vocabulary builder, he's put down 3 days, but he's very unconfident. He's put 10%. And it's like, sorry, I shouldn't laugh, but what does this say? What does that even mean? It's like, it's some sort of indication that, I'm just remembering the discussion about this, so I got very excited. Right, we can fit a distribution to this. But this was really overkill. The person didn't, it was interesting. Like, I was very keen to find situations where we could use probabilities, but this person, he's just using this in a very rough way to indicate his uncertainty about 2 and 3. So I would not now jump to conclusions about what those numbers mean. And then we got some findings. And of course, this is too small for you to read, and so we'll try. Because I'm an optimist. Okay, that's a little better. These are, right, so I promised you types of uncertain data. Here are some types of uncertain data. So the most common one, yes, I knew it would do that. The most common one is estimate. About half of of all the uncertain data we discovered is what's called an estimate, which is data that's approximated by the user of which the precise value is not known. So like for example, the expected number of attendees to an event, or I suppose the number of Valentine's cards that people are going to want to buy. So half of all the uncertainty we found was of this sort. So in a way, this is positive if we're trying to apply probabilistic methods here, because you would think that probabilities would help. And so here's the kind of quote. We're talking about the future. We don't know exactly what's going to happen. All we can do is make best estimates. And then the other ones are like dynamic data, which is data which changes over time. And so stuff to do with the stock market is a good example of that. And it's got a concrete history to it. And then there's errors, data that contains an error, so it might actually just be the formula has returned an error. There's missing data, for example, which is just missing from the spreadsheet, such as gaps in data. So unfindable data, this is interesting. This is data that's actually in the spreadsheet, but the person can't find it. And that stops them getting work done. You know, it's there. So the example we got was, it was some kind of timesheets, and the person wanted to know how many of them had taken place at the weekend. And if they'd been capable of writing a formula that could do, I'm not sure I could do it. I mean, it's quite hard well, you have to have the right, you have to have the right functions. But the person had dates and hours worked. But how do you go from a date to figuring out whether it's at the weekend or not? So, you or I could spend some time looking at the manual and figure out the functions that do this, but this was beyond this person. And so as far as they were concerned, it was uncertain data. They don't know how much was done at the weekend. And then there's untraceable data, which is just, they've just lost the date where it came from. And so they've got it, but they don't really know its origin. So it's a problem of provenance, if you like. It's there, but they don't really believe it. Okay, I should keep going. No, technical problems. Just click, will it do it? This maybe. Come on. Sorry about this. Oh, that. Yes, that's it. I see. Okay, and then categories of coping strategy. So, slightly, one coping strategy is actually to add some more by say using approximated values, or like if there's missing data, just let's put an approximated value in, such as an estimate. That was pretty common. Or to communicate it. So again, we asked them overall, what is your coping strategy? I mean, they're trying to do something with the spreadsheet. And so a classic one is that we found several people say that their bosses didn't want to know about the uncertainty. We got a quote about the boss says, just give me a number. I don't want to know the uncertainty. It's your job to deal with the uncertainty. So it's interesting. So this is I think this is quite a common situation where people take time. The subordinate takes some time to analyze a situation and maybe tries multiple scenarios, or maybe actually does probabilistic modeling, but ultimately their job is to kind of reach a decision, make a good recommendation, and be prepared to stand up for themselves and back it. And so when they go to their boss, they're going to say, okay, the number is 120. It's not like maybe 100. The boss wants certainty. So that's communication. The user communicates it by basically diminishing it. Exploit. The user uses the amount of uncertainty in a spreadsheet as a valuable piece of information by adding weights to missing values during model building based on how often they were missing. So you actually can exploit it. Ignore it. You just ignore it. Remove it from the spreadsheet. So that happened quite a bit. The user minimizes uncertainty So they actually do some work to minimize it rather than just ignoring it. So they'll acquire more data, discuss with colleagues, maybe find the person who had has left the company and get them to tell them, where this data actually came from in reality. And then there's understanding it. Again, maybe reading the literature or doing things like plotting the data, evaluating the data source, and so forth. And actually, so I don't know the citation here, so some of these coping strategies came from a paper at CHI recently that was looking at sources of uncertainty in general in data analysis, not in spreadsheets in particular. So we found some additional ones. I should have put the reference in. It's in the paper. Okay, so that was a study. Basic findings from the study. Then what are the implications for design? So this is where I'm going to tie things together. I've told you about the sort of three categories broadly of technical approaches that we might take to uncertainty, which is like the qualitative, like the estimates, like the possibilistic, like multiple scenarios, or the probabilistic that I've been talking about. And we've got this chart that I will talk to you about. So we've got a matrix. So there's three kinds of technical solutions we might propose, and then there's these six kinds of uncertainty, and we have somewhat qualitatively and subjectively put them on a scale of none up to good in terms of how well it supports the kind of uncertainty. So we reckon. If we look at, say, the probabilistic, this bottom line, we think that probabilistic is definitely good for dynamic data. So that was cases like where you're maybe looking at, say, so stock markets. I mean, that's, as long as you know what you're doing, that's a sort of reasonable place where you could use probabilistic models, though you need to watch out, obviously. But other places, maybe they've got missing sensor data, where, again, if you've got a history of that sensor data, you might well be able to use probabilistic models to make a prediction of the missing types. On the other hand, and I think this is like maybe a big takeaway for me, is that 50% of what we saw were estimates. And I can't honestly say I think that probabilistic modeling of the sort that I've been arguing about is good for that kind of estimates. So for me, this is a bit of a negative result, because I was kind of hoping otherwise. But I don't think the people, when we look at the occurrences of estimates in the transcripts, I don't think the way the people were talking about that makes me think those people could actually plausibly and confidently come up with distributions for those missing values. So maybe that's a negative result. On the other hand, the use of possibilistic approaches like multiple scenarios fit very well dealing with estimates. And so I think that's good to know. Let me see. So that's it. I'm not going to go through that in detail. I think maybe what I would say, I've just said that. These are the ones that we thought were particularly good. So qualitative for estimates. I mean, yes, it's a good fit, but I'm not sure if it brings an awful lot of value just tracking the fact that some values are estimates. I think some more work need. I mean, so we haven't at this point actually taken these methods and applied them to the user's spreadsheets to see how well they were doing. So this is more like a pencil and paper exercise in the lab after having spoken to the users. And so it could we might well go on to do that. But this is what we currently have. And I think, so possibilists for estimates are good. Probabilistic for dynamic data is good. And say probabilistic for errors, there seems to be some evidence for that as being useful. Okay, and I've got one quote. So recommendations. I think recommendations for design. I would say that no single formalism is able to solve most of user problems, which suggests offering multiple features for dealing with uncertainty. Qualitative tagging is most applicable, but frankly, it seems to have low value. I would say if you're sort of adding, this is maybe debatable, and in fact, in our team, this is a bit debatable, but if we were going to exclude one of them, it might well be possibilistic on the basis that spreadsheets already are quite good at dealing with multiple scenarios, if you know what you're doing. That's maybe subject to debate, because after all, bothered to put the scenario manager into the system, suggests that at least at some point, people thought the scenario manager would be very useful for and better than having multiple columns. So I think that's possible. And then things like unfindable and traceable data need maybe different techniques, like maybe some sort of natural language ways of constructing queries, say for dealing with this problem, weekend data. Reflections. My last slide. We're coming to the end. So it's kind of like there's sort of good news and there's bad news from the point of view of end-user probabilistic programming. The good, in fact, it's been there before probabilistic programming languages, and the at-risk guys seem to reckon they've got 500,000 users. That seems plausible. We do encounter quite a few people who use at-risk. The bad news in terms of like taking probabilistic programming language technology and putting it into spreadsheets, at the moment I think the bad news is that most of what people regard as uncertainty isn't suitable for being dealt with by probabilistic modeling. One serendipity that came out of this was we didn't initially think about using SDFs as a tool for dealing with uncertainty, and SDFs after all are implemented in no major spreadsheets. But we found a new application of SDFs. There's very little in the literature about SDFs. There's like one paper, and then there's a textbook on spreadsheet technology that does an implementation of SDFs, but doesn't do very much with them, in fact. So, pardon? Sheet-defined functions. So this idea of using SDF, I mean, it's already a general-purpose tool for doing lots of things, doing functional programming. But if we had it, then it would be a nice way of dealing with both possibilistic and probabilistic uncertainty. At this point, we were not really seriously thinking in the study we were doing and the kind of technologies we were adopting about full-on probabilistic programming, actually having end users do conditioning. And that's kind of, in a way, it's really exciting. I mean, I would love to be able to use a spreadsheet to do full probabilistic programming, but I'm not sure how many people would really want to do that. And so Frank Wood's company, I'm sort of vaguely pointing at the guys from UBC, in VREA, tried to do this, and they presented themselves as being a sort of Bayesian version of at-risk. We're saying it's like at-risk, but even better because your models adapt to the actual given data. And I think they had trouble making that case, but I don't know completely why. I'm not sure where that is going, but it's very intriguing and something to watch. And finally, I really enjoyed doing this thematic analysis. It was new to me. I found it a little bit messy. Like I say, the different categories we have, I think, are a little bit fluid because it was only based on 11 people. And it would take more research and more time and more interviewees to make them finer grained. On the other hand, I feel like I'm pretty confident in this negative result that we got quite a lot of evidence from this about whether people would actually want to do that. So that's good. So so this thematic analysis is, I'd say it's complementary to sort of PL theory, like say, I don't know, the regression calculus I was talking about yesterday. And it's probably a better guide to actually what's useful, talking to people. We thought that probabilistic programming, say even with, would be super useful for lots of business cases. And you could make these arguments around the flaw of averages in the abstract. But then when you actually look at people, it turns out there's maybe not so much of a demand, which is sort of interesting to know. Okay, that is it. You've had 3 sessions from me. I won't attempt to summarize it all at this point. But if you have any final questions, I'll be happy to take them. Or, yeah. I've talked to lots of different people. I guess it's the question whether, when someone who's capable of learning Bayesian learning, whether they'd be better off with something like Stan or Bugs or Infer.net, or whether they want to do it in the spreadsheet. And that isn't really, that's not completely clear to me. just yet. Like, I mean, I speak to people inside Microsoft who do some estimation of how many computers to buy and disks to buy for Azure, and they'd love to be able to use probabilistic programming to do that. And they actually were really keen to use spreadsheets, because a spreadsheet is something you can easily pass around in an organization. And you can, spreadsheet is a great presentation tool as well as a modeling tool. So if they write a stand program, that's fine, but maybe they embed it in a Jupyter notebook and pass that around, but that maybe won't work with some of the less technical people. Whereas if they do all the modeling in the spreadsheet, then it's a nice self-contained thing that they can give to people, and it hides all the stuff. So that's a cause of hope. But Sarah, you had a question.
Yeah, I'm curious if you, like as a result of the user study, extrapolated any opinions about just like the designing the semantics of like spreadsheet languages in general. So not just with respect to probabilistic programming, but like the models maybe for predefined functions or otherwise, like how users interact with the language.
Not specifically from that user study. We weren't really offering new technologies at that point. We were really just asking, what are people currently doing?
Or I guess
so,
from not just that study then, but like all of the work you've done on that, like what are maybe some design implications from a PL perspective for like languages?
So we've a bit of work. Let me see. We looked at sheet-defined functions, and it started asking, well, how would you use these in practice? And we found there were often cases where what you wanted to do was to take a model, let me see. Think of the sheet I showed at first that had 10 rows in it, and it's showing the flaw of averages. And maybe you make that into an SDF, and you would maybe that's not a good. Let me. What I'm saying, but it doesn't matter much. You take that, and you would maybe like it to work with different numbers of rows of samples. And in the standard notion of a sheet-defined function, you can't do that. The grid you get has the same shape as the one you start with. But we found it to be often the case where you've got a sample grid and you like it to sort of stretch to fit some data. Maybe you want to have the number of rows be the same as the size of an array that you pass it in, and you like it to sort of fit to it. So we came up with this notion of elastic sheet-defined function, where the input ranges that it works on can kind of stretch. And the way they do that is the way a human would stretch a spreadsheet. They would drag fill the formulas further, so they fitted the whole input ranges that they have been given to. So that came to us by actually thinking about how people would actually use SDFs, and so we have a paper about that with this quite a lot of big technical development on how you can do this, and also we did a user study on it to look at how it compared with alternatives. So the alternative would be using maps and folds, and instead what our mechanism does is it just automatically fits the sheet-defined function to its input data. And we found that users much prefer this happening automatically than for them to have to learn higher order programming with maps and folds, which is sort of beyond them. So that's one, I guess, PL insight that came from looking at actual use cases of spreadsheets.
So the changes that you made the function periodic, or you made it automatically expand to fit the...
It's more they automatically expand to fit. Because if you think about it, a spreadsheet has got, this is like a completely separate talk, but a spreadsheet often will have, we call them tiles, bits of the grid that have replicated formulas. And very often you've got maybe 2 bits of grid that have the same number of, say, columns or rows in them. And if you want to and so you might want to automatically kind of resize the grid so that it fitted some input data. I suppose I can't say it's all about quantities, I suppose. I mean, I think there's plenty of people in the world who could do this. But if you think about them as a fraction of the number of people who can use spreadsheets, I think they're quite small. Whether
Even if people were educated and they knew the Bayesian stuff, they knew these distributions, is it still a problem? Is it just they don't know enough of the technical stuff and they need to learn it? Or is it more like a modeling problem, where it's just for many of these scenarios, you think people just have trouble trying to give good models for these estimates? That would make sense.
I think it's a bit of both. I mean, there's a lack of education. People are uncomfortable with probability distributions. That's one problem. And then the other one is, in fact, the gentleman was asking about this, is that it may be just hard, but even an expert in probabilities might have a hard job thinking, what are the parameters for the distribution I should give at this point? So sometimes you get lucky and you've got a lot of past data that you could learn from. And I think that case will get more and more important, actually. And so that there is hope there, I think, where, given a lot of data in a company, in a spreadsheet, you could perhaps learn how to fit distributions to it. Okay, it's 5:20. It's been a great experience for me. I hope you enjoyed it. Thanks so much for your attention.